Hi, and welcome to Module 4 of the Introduction to Dask tutorial, in which we'll take a closer look at performing machine learning at scale with Dask. In this module, we'll start by talking about when to use Dask for machine learning. We'll then take a closer look at the DaskML syntax, train some models with DaskML, perform hyperparameter tuning, and look at the xGBoost and Dask integration. I'll be working through a Jupyter notebook that you can access at this link. All right, so I've got the Jupyter notebook open for Module 4, Machine Learning. So far in the previous modules, we've seen that Dask scales data analysis with parallel computing through things like Dask data frame and Dask array. This module will zoom in on the specific use case of using parallel computing to scale machine learning. We'll cover a few things. We'll start by talking about the different types of scaling problems in machine learning. We'll then dive deeper into each one, looking at compute-bound problems, memory-bound problems, and the specific xGBoost Dask integration. Let's start by talking about the different types of scaling problems in machine learning. There are two main types of scaling challenges that you can run into when doing machine learning at scale. You can either run into issues with the size of your dataset or with the size of your model. The first problem is a memory-bound problem. Your data no longer fits into your RAM. The second problem is a CPU-bound problem. Your data fits in RAM, but your training or your hyperparameter optimization is taking too long. In both of these cases, you could benefit from using parallelism. And here's a handy diagram that can visualize some of these problems. On the x-axis, we have the data size, and on the y-axis, we have computation time or model complexity. As long as you're in the bottom left quadrant, you should not use Dask. You should use scikit-learn or your other favorite machine learning library. Once your dataset increases beyond what your machine can handle, or your computations or training or hyperparameter optimization is taking longer than you would like it to, then you end up in the top two or far right quadrants, and you should give Dask a try. Before we continue, a quick refresher on the scikit-learn API. Just like Dask data frame plugs into the existing pandas syntax, and Dask array does that with the NumPy syntax, DaskML is built to closely follow the scikit-learn API. The thinking here being that people know and love the scikit-learn API already. We just need to overcome the scaling problem. So we'll start by using just scikit-learn, no Dask here yet. We'll generate some synthetic classification data and store that in two arrays, x and y. Once we have this data, we can instantiate a scikit-learn estimator, in this case a support vector classifier, and fit that estimator on our data using the familiar and popular scikit-learn syntax, estimator.fit. Once the model has been fit and trained, we can inspect the learned features and check the accuracy of our model. Now, a common next step in machine learning pipelines is to perform hyperparameter optimization. And one way to do that is with grid search CV. So we'll import that from the sklearn library and create a grid of, in this case, 4 parameters that we want to try out. The goal here being to find the best parameters that will increase the accuracy of our model. We'll instantiate the grid CV object and again use the scikit-learn syntax to fit the grid search CV on our training data. Because we have 4 hyperparameters, we have 8 possible combinations, and these 8 fits are being trained sequentially, one after the other by default. This is fine for now because it's a small data set and a small number of parameters, so the total fit takes 16.7 seconds here. But you can imagine that if your data set increases, or if you wanted to search over more hyperparameters, that you might want to run this in parallel, because each grid search CV training is a separate, independent process. Once this is done, we can inspect the best parameters and the best score. Hyperparameter optimization can quickly become a compute-bound problem as you increase the amount of hyperparameters, combinations that you want to try out. Scikit-learn already has a parallelism component built into a lot of its estimators that gives you access to single machine parallelism. Any scikit-learn estimator that exposes the njobs keyword can be trained in parallel. setting this keyword to -1 will use all of the available cores in your machine. So let's run the same grid search CV computation that we ran above, but now using the njobs keyword to run it in parallel. Again, we're doing 8 fits, 8 different combinations of hyperparameters, but these are now running in parallel. And as you can see, this runs quite a bit faster than the sequential version. You'll notice that there's still no Dask here. We have parallelism, but we're accessing it through joblib. Dask becomes useful here if we want to scale beyond our single machine. In that case, we can instantiate a Dask cluster, in this case of 8 workers on our local machine, create a more ambitious parameter grid, and instantiate the grid search CV model. To have joblib and Dask communicate to each other, we'll import joblib and create a context manager specifying the Dask parallel backend. And we'll then fit our grid search CV within that context manager. This is now fitting 72 different combinations of hyperparameters. And it's doing that in parallel. This took about 27 seconds. But actually, we're still just working on our local machine here. We created a Dask cluster, that's right, but it's the 8 cores in our machine, which is the same as we were using before with joblib, which was also accessing all of the 8 cores in our machine. We would only really start to see performance benefits here if we were able to scale out to a remote cluster with Dask. We can do that quite easily by connecting to a Coiled cluster. In this code, we're connecting to a Coiled cluster that's already running in the cloud, and then pointing Dask to run all future Dask computations on that cluster instead of on our local machine. Once that's done, we can copy over this grid search CV code that we were running before. And because joblib knows that it needs to use Dask to run this grid search, it will now run these Dask computations on our Coiled cluster in the cloud. We're again fitting 72 combinations of hyperparameters, but these are not running locally on our machine, but on our Coiled cluster in the cloud. And that cluster has 10 workers with 4 cores each. So we've got a lot more compute power here. And as you'll see, this computation completes faster now that we've run it on our remote cluster. All right, so that we just saw a few examples of compute-bound machine learning scaling problems. Let's now move to talking about memory-bound scaling problems. These are problems in which your dataset is larger than your RAM and cannot be loaded into memory. So what we need to do here is find a way to cut that dataset up into smaller chunks and process chunks of the dataset in parallel. As we've seen before in the previous modules, this is exactly what Dask is good at. And this is what the Dask ML library does. And just like Dask arrays and Dask data frames mimic the NumPy and Pandas syntax, respectively, the Dask ML library is designed to stay very close to the scikit-learn API and syntax so that it looks and feels familiar. We'll start by making some imports and then create some synthetic regression data. This is stored in arrays, but these arrays are now Dask arrays rather than NumPy arrays. And as we saw in Module 3, each Dask array is a collection of multiple NumPy arrays. We can then create our train and test splits and instantiate our Dask ML model. Time for a first exercise. Can you fit this parallel Dask ML linear regression model on the training data? Take a few minutes to think about it and maybe try some code out. And you can always uncomment and run this cell to load the solution. Let's take a look at the solution. The syntax is here actually identical to the scikit-learn syntax. We call our model and call the fit method on that model and supply the training data. This linear regression model is now being trained in parallel. Time for another exercise. Can you use this linear regression model to make predictions? Again, take a few minutes, think about it, try some code out, and you can always uncomment the cell and run it to load the solution. All right, let's take a look at the solution. Again, the syntax here is identical to scikit-learn. take our model and call the predict method, supplying the data that we want to use to make our predictions. Once that's done, we can use the score method to get the accuracy of the model. To finish up, let's take a quick look at the xGBoost and Dask integration. So while the Dask ML library implements some of the most popular machine learning algorithms for parallel computing, it doesn't include all of them. For xGBoost, the maintainers chose a different approach. They built a Dask backend straight into xGBoost so that you can use Dask to parallelize training of xGBoost models without leaving the xGBoost library. Going through this in detail is beyond the scope of this module, but I did want to show you some of the code to get a sense of how easy it is to use Dask to train your xGBoost models in parallel. Once we've imported xGBoost, we create our dtrain and dtest d-matrices. These will be familiar to you if you have worked with xGBoost before. We just have to specify that we're using Dask. The same goes for training our xGBoost model and making the predictions. There's a link here to a detailed step-by-step tutorial if you're interested to learn more. All right, that wraps up the fourth module of the Introduction to Dask tutorial. We looked at when to use Dask for machine learning problems and the different types of scaling problems you might encounter. We looked together at the Dask ML syntax and how it mimics the scikit-learn syntax. We trained some models with Dask ML and performed hyperparameter optimization. And we took a quick look at the xGBoost Dask integration. So what's next? Well, you've finished 4 of the 5 modules in this course. There's only one module left, in which we'll talk about parallelizing Python code with Dask delayed. I'll see you there.